Okay, so let's review some materials in machine learning. So one of the most important materials in machine learning is linear algebra. So as I said, it heavily relies on linear algebra. It's very essential to understand what vector matrices and what kind of operations that we needed to perform with them. So the simplest things that you probably have learned, this is vector in Python. So everything just being, you can think about as multi-dimensional array, and its array. So basically, which is the most convenient way is to using NumPy. So it's packaged in Python. So what you can do is you can say like import NumPy as NP. So all you need to do is you can define the vector as follows: b equal to np.array. So this is actually an array. So this tells you the v is equal to like this. So this with 3 dimensions. Let's start with the 4 dimensions in R4. Right, so this is fairly straightforward. So what you can do is you can denote this and call this like ith element, which is vi. And what you can do is you can just call, say, and say like if you want to know the shape of the kind of vector, so you can call the v dot shape, or the or similarly you can do like like numpy dot shape of v. Let's say same thing. It will actually output this 4 comma, so that indicate this is a vector. Okay, so this is fundamentally different. If the output is 4, 1, this is actually a matrix. So this is fundamentally, different. So this is a vector, it's 1D, and a vector, this is 2D matrix, but just happen to be, we only have a 1 column. So, but like for the vector, there's no, nothing about a row and a column, just a vector, right? So it's just a vector, and it has nothing to do with the row and the columns. But the matrix, and this is a 4x1 matrix. And also, this is different between 1x4. So basically, this is a column, and this is a row, right? So this is, fundamentally different in, NumPy, and you should never use the size, and this is things that you should never use here. And if you want to assess the third entry of this vector, you should call this v2 right here. So this is basically says, and everything start with 0. So this is 0 index, 1 index, and 2 index. So if you want to assess 3.25, that would be second index. Okay, so and you can also do a plot. So what you can do is you can just simply import matplotlib library, which is a very popular library being used. So you can just define this 2D and a 2D vector, 2, 5, and 3, 1, and print it out. So this is the way to actually print out this point. So you can see this is 2, 5, and this is 3, 1 right here. Okay, so we just simply plot out with this and with this like scatter functions right here. So you can use these kind of functions to help you to do any kind of illustrations if possible. It's always a good idea to using plot to illustrate your ideas, and this is techniques that you need to learn. This courses as well. All right, so and also like this actually represent as a like vector, which is 2, 5, and 3, 1. And the vector can also be represented by the arrows. So what you can do is you can write this as separate functions right here. So this is some like separate function. You can write as like exploratory like functions. You can go and to check what kind of function that we're working with. The Jupyter notebook. So this is the function that that we handle with. But if we like call this like and a tiny and the functions that we are getting, we're actually getting to this like vectors clearly. So this is basically 2, 5, and then this is 3, 1. So this is another way to illustrate that, because for a vector you can either illustrate with the vectors arrows, or you can just like illustrate with a point and assume you're starting off the vectors from like origin, which is 0, 0. Okay, so next is more mathematical term, which is called norm of the vector. So this is just being like initially like defined as the measure of the length. So basically the magnitude of the like vector. So basically, abstractly speaking, a norm is actually a function that map from the vector Rn into some non-negative real numbers from 0 to infinity that need to satisfy these three properties, which is it's non-negative and is 0, and only if x is equal to 0. It has to satisfy the triangular inequalities. It also need to satisfy and the linearities. We can move the alpha out if alpha is positive. There are multiple choice of norm. We will talk about this norm a lot, but the most common one that is the Euclidean norm, which I believe you will be very familiar with that, which basically is square of each component summed together, then take the square root. This is also some other more norm, for example, P norm. P can be chosen from 1 to infinity, and 2 is included. But of course, you can choose infinity, which turns out to be the maximum value of each component. There's another one, which is one norm, which is just simply summation of absolute values of each component. Okay, so this is one norm. One norm, infinite norm, two norm, they are all very popular. You can calculate this one norm, two norm, and writing a separate functions. So this is a function that we use, and I use something called comprehension to calculate the square of each component and sum them together, then square and take the square root. So you can see if I have a 2, 5, this is my vector, it can output the vector norm right here. But obviously this is not efficient. So what you can do is you can using linear algebra module. So this is called LIN ALG, which is linear algebra, and the shorthand for the linear algebra. So what you can do is you can just call like import this like linear algebra as LA. You can say LA.norm of U, which is automatically calculate the two norm of the vector U. You can also calculate the one norm, which is, and by default, this norm is two norm. So this is equivalent as LA.norm U2. So this is basically by default is two norm. But if you want to do like one norm and you need to specify this as one, you can do infinite norm as well if needed. Okay, so next is dot product. Dot product is so dot product is it basically says it's like inner product in terms of the Euclidean spaces. It's defined as the following. So basically, normal U times normal V times of the cosine of the theta. Theta is the angle between the U and V. So basically, if this is U, this is my V, and the angle between that is theta. So, and if U and V are orthogonal, if U transpose V is equal to 0. So that means if this is U, this is V, the angle here is 2 and like pi over 2. So that means it's 90 degrees. That means this is, I'm actually orthogonal. And let me just write it down like more clearly. So this is U, this is V. This is an orthogonal if the angle is pi over 2, since cosine pi over 2 is equal to 0. So the dot product of U and V is precisely equal to 0. Okay. And this is also, if this whole set of the vector U1 to UK, it's called orthogonal if they are pairwise orthogonal. So that means UI and UJ, and inner product of UI, UJ, they are equal to 0. Also, by the way, so U dot V, we can also write everything like U dot V, and we can write as U transpose of V as well, because we can think about U and V are columns vectors. Right, so this becomes a row, and multiply a column that's a scalar. If it is pairwise orthogonal, then we call the whole set is orthogonal. And also, if this is and each count, and if like each and a vector has a one like norm of the vector is equal to 1, and then we can further call this orthonormal. So this is very important. We are going to using and a lot of and factors and for the orthonormal here. Inner product, it's pretty straightforward. So this is like, and everything that just like do it and explicitly. So this is and if you run everything from scratch, so this is dot product, but obviously that's not efficient. We can make it more efficient if needed. You can call this MP dot UV, which is just automatically do like dot product for you. Or you can do U dot V or V dot U. It's like symmetric, doesn't matter. So like NumPy do it for you automatically. But I want to emphasize multiplication. It's not a product. If you do the multiplications, it's element-wise multiplication. So basically U times V, it just element-wise multiply them and multiply them together. It actually gives you vectors. Not a scalar. Projections, this is not, we didn't use that too much, but just give you some idea. So, and if we want to project this V on the directions of U, so this is how you do it. And if you project on the direction of U, so this is the projection of U right here. So what we do is this will be equal to U dot V, and divided by the square of the norm and times the vector of U. So basically this is on the direction of U. So this is the scalar. This is multiply a vector. So this is actually a vector in the directions of U. Then it's a matrix. So you can think about, we can stack all these vectors into rows or columns. This becomes a matrices. So you can see this is very straightforward. This is 2 by 3 matrix. Right? So I assume you already know everything very well. So we have 2 rows. We have 3 columns. And all the index start from 0. So, and you have to be careful. And for example, this is 3 by 3 matrix right here. And you can do B, and right here is 2 by 3 matrix. You can just print them out without any problems. So you can do, again, you shouldn't you call it size, that's a bad idea. Don't ever do that, because it gives you not the things that you want. You can call the A dot shape or like NumPy shape, and for the A. So like A dot shape, it actually give you 3 by 3, because this is actually 3 by 3, right? 3 rows and 3 columns. 3, 3. That indicate I have 3 rows and I have 3 columns. And also indexing. So indexing obviously is very important. So this is, like for example, this is an x32. This is the 3rd row and the 2nd columns. So this just give you how to index those and the matrices. So this is fairly matched with the how we do it, like one NumPy, but the difference is here we start with a 1, 1, but in NumPy everything starts with a 0. So this is the difference, major differences that you have to keep in mind when you're doing these kind of and matrix operations. In Python NumPy, everything starts with a 0. However, in like mathematical notation, it usually starts with 1. So this is a like index shift from 0 to 1. All right, so so you can do print of A. You can do like 2nd row, 3rd columns. It actually, if you want to do it, it's like A1, 2. And I mean, every like index shifted by 1. You can just call this 2nd row, which is give you a vector. So that means that will be A1, comma, column. So this column actually tells you I'm actually interested in the whole row of, and you output as a vector. So this is 3rd column vector, which that means I'm going to get the last column vectors, but I want all the component of the rows. So this is the column here. You can do like all the things if you want. It's just fairly straightforward. But there's one thing that you have to be careful. These two are actually different. Okay, so this is column 2. It actually gives you a vector. But if you put 1 as bracket here, it actually treat this as a matrix. So this will be a 3 by 1 matrix. However, this is 3, 0 like vectors. So this is fundamentally different. Whether you put bracket or not, it gives you different result. Okay, so you can see right here, this actually shape is 3, 1, which is the matrix. It's 3 rows, 1 columns. This actually gives you just 3. So that means it's actually a vector. Matrix multiplication, I assume you already know all of that. And what is rules for the matrix multiplications? It should be a fairly straightforward and operations. So this will be A dot F or F dot A. They are doing matrix multiplications. But in matrix A and multiply F is not equal to F multiply A, right? So this is because A and F are both matrix, but they don't commute with each other. But A times F, this is element-wise multiplications. So this is always element-wise multiplications, not matrix multiplications. So matrix multiplications, you have to use dot. Right? So this is fundamental difference. It's very important that you know everything well. Otherwise, we are like chasing the wild goose. So you need to know the differences very well. All right, so let's and then let's continue. So as I mentioned, 1D vector is actually 1D, right? So there's no such kind of thing, whether it's a vertical 1D or horizontal 1D or row 1D or like column 1D. There's no such kind of things. You should not surprise if you're trying to transpose. So this is a notation of transpose. if you transpose of a vector, it's give you the same thing because there's no row like horizontal or vertical. Just u dot transpose itself. However, if you put a bracket, and then that becomes automatically becomes a row vector, 2, 5, right? So this is 1 by 2 matrices. Then you can take the transpose. Then this becomes 2, 5. So the top one will be row, bottom one will be column. All right. So there's some interesting examples here. For example, this is 4 by 3 matrix. This is a 3 and the vector. So this is 1 by 3. So you can see this is 4 by 3, 3, 1 by 3. For A dot B, so you can do it, not a problem. So this is actually give you a size of 4, right? So this is actually give you a size of 4. Not a problem. So right here, sorry. So right here. So this is, I'm actually give you a vector. But you can do it A dot C transpose. So this is actually give you a matrix. So so that actually give you a column matrix. So this is fundamentally different. A times of B, A dot, let's say dot B right here. So there are 2 ways to interpret it. So the first way is this is a vector. So then the output is a vector. So if A dot B, if this is a column matrix, so this actually gives you column matrix as well. So this is something that is and very helpful and very helpful for you to understand everything. But there's some fundamental things. So this is kind of interesting. So A dot B, so this is actually a vector. So this is A dot C transpose. So this is matrix. A vector subtract a column matrix is not equal to 0. It actually gives you a matrix here. This is a 4 by 4 matrix. I saw many people make mistake all the time on this type of problems. So you have to be very sure what kind of structure you are working with, whether you are a vector, whether you are working with like matrix, column matrix, row matrix, what kind of matrix you're working with. However, if you turn this into a row, you can do and other things. That becomes a matrix, subtract a matrix. So this is a 2 columns matrix, subtract a column matrix. Then this is precisely equal to 0. All right. And then you can work with the norm. So this is, and a matrix you can work with norm as well. You can work with the Frobenius norm, you can work the 2 norm. So there's like, and a lot of like different choices of norms that you can work with. Rank. So I think you probably have and heard about a work about the rank. So column rank of like matrix is equal to the row rank, just call it rank. So what you can do is you can do and find out the rank. For example, this is U is a like column vector, V is a row vector. If you do U dot V, so you like, and this is 2 by 1, this is 1 by 2, this actually give you 2 by 2. But the rank of this whole thing is actually 1 right here. Okay, so this is something that should be aware of. SVD, and I assume you already know that as well. So this is just a quick recap of SVD. So SVD is basically a decomposition of the matrix for any matrix. M by N, we have M rows and columns. So we have a rotation matrix of U, another rotation matrix of V. So U and V, they are all orthogonal matrices. And the sigma here is actually a diagonal matrices. So so this is and the diagonal and the matrix and all the entry on the diagonal, they are non-negative and non-increasing. So basically, we have a largest singular value, we have a smallest singular value. So the largest singular value, sigma 1, smallest singular value, sigma p, they are all strictly and non-negative, and you can order them and decreasingly. So this is basically a basic structure of everything. U and V, they are orthogonal. What does that mean? Is U transpose is actually identity of M by M, and the VV transpose is actually identity of M by N. So, I mean, the way that you do it is you can just call it LA dot SVD. So this is simple, like to process the singular value decompositions of the matrix of F, the U diagonal part, and the V transpose. So I want to emphasize the way you got out is actually the V transpose, not a V. Okay, so you got, and you can just do like U dot S diagonal and the V transpose. It should come back to the original matrix of F right here. So and you should get precisely the same F you get, which is you can see right here is the same. All right. So you can see right here, S diagonal actually just give you the diagonal component of my singular values. So they are all singular values. They are not that actually singular matrix. So sorry, the sigma. So like sigma right here in this cases will be just 2, 0.5. I put 2 zeros right here. So, and that's why you argue, and you need to put a diagonal for this vector here. All right, so this is singular value decompositions. There are interesting properties for those singular value decompositions. For example, I mean, this always exists. So this is really good. No matter what kind of matrix you work with, it's always exists. The number of non-zero part equal to the rank of A. So basically, for example, right here, you can see we have 2 non-zero parts. So that means my rank of this matrix is actually 2. If so we can rewrite this matrix into the form of like this, right? You summing I from 1 to P, sigma I, Ui, Bi transpose, right? So this is actually sum them together. Ui is called left singular vector. Vi is the right singular vectors. So that's why, so and you can think about if A times a Ui is equal to sigma I Bi, that's the by definition of the and like left singular vectors. All we do is A and the dot Vi sigma I of Ui. So this is the right singular vectors. Right? So this is basically these two things. And how we actually calculate the U and V, right? I mean, if we actually augment everything together, so do I getting U1, U2 to UM. So this is basically the, and if we put them together, and V is actually V1, V2 to Vm. Okay, so the way that we calculate these things is the following. So you can using this trick that we know A is U sigma V transpose. So I'm going to do AA transpose U sigma V transpose V sigma U transpose. Right, so this is basically how you calculate this. But we know V and V is orthogonal to, so that means V transpose V. This is actually identity. So this becomes U sigma square U transpose. And similarly, an A transpose of A, it becomes V sigma square V transpose. Is it right? Yeah, that's right. So basically, U is eigenvalue. So I mean something called eigenvector of AA transpose. V is the eigenvector of A transpose A. Okay, so this is something that is extremely powerful. All right. So that's how we calculate U and V's. And also you can see right here, I mean, this is eigenvalue decompositions for this AA transpose matrix or A transpose A matrix. So these sigma square is actually the eigenvalues of AA transpose or A transpose A. So that means my singular value of A are actually the square root of A transpose A. So basically, I mean, they are all diagonal matrices anyway. Just take the square root of the eigenvalues of A transpose, that will be singular values that we want. So this gives you some idea how we actually calculate the singular values of A is the way that we can just take the AA transpose and do eigenvalue decompositions. And also they have some like interesting properties. It's basically says, so this is very important in PCAs. So if the matrix A, so we write so matrix A as the following. So this is basically sigma j is the singular values, uj is the left singular vectors, vj is the right singular vectors. And of course, I assume everything that I'm talking about is a review. So basically, you should have learned that in the previous courses. So if you didn't learn that, this is something that you need to make up before attending or taking these courses. So so the key here is if we take the partial sum, instead of like R is the rank of the A, right? So if we pick the K that is smaller than R, so that means I only take partial sum, which is AK right here. So that means I only take the K sum instead of R sum. That actually can capture as much energy as possible. Mathematically speaking, is if we want to find out an X that minimize X minus A in terms of Frobenius norm, but I restrict my X to have the rank is less or equal than K, it turns out the best approximation is just being the K partial sum of my singular value and singular vectors. Right. So basically, this gives me idea this AK is nothing but the optimal low rank approximations of this specific matrix. Right. So this is considered to be optimal. So this is something is very important. And then later on, we are going to using these factors and fact in the PCA, principal component analysis. There are some other things I think we have already talked about, eigenvalues and eigenvectors. So if the matrix is square, you can do eigenvalue decompositions. You are and basically and decompose the matrix into U lambda U inverse. And the most important part is actually the trace of this M. I mean, sorry, this should be M here, right here. Is actually the summation of the and the summation of the eigenvalues. So the trace of the M is equal to the summation of the eigenvalues. If this is a symmetric, we can further make it like simpler because, and for the symmetric matrix, its eigenvalue decompositions is further simplified to be U lambda U transpose, and U becomes orthonormal matrices. And the most important part is if all the eigenvalues are non-negative, then A is called PSD, positive semi-definite matrix. If all the lambda is strictly positive, that becomes a positive definite matrices. Okay, so this is something that you should be aware of. And the way to call to eigenvalue decompositions is very simple. Just linear algebra module .eig. It gives you eigenvalue and eigenvectors. So we actually through this we using eigenvalues to define what is positive semi-definite and a positive definite for the symmetric matrices as well. All right, so this is basically some simple things that we work with. All right, so I think that's everything I want to talk about for the linear algebra in this portion. So in the next part, we're going to talk about the an optimization and the vector calculus.